Welcome to Engineering the Quantum Semiconductor, a deep dive into the physical architecture, material components, and three-dimensional packaging of silicon spin-qubit quantum processors. What you're seeing here is not science fiction. This is a real engineering blueprint, a cross-section of the chip technology that could power the next generation of quantum computers. The key argument of this entire presentation is simple. Silicon spin-qubits do not require us to abandon the semiconductor industry we already have. They require us to push it further than ever before. By the end of this video, you will understand exactly how a quantum processor is built, from the choice of atoms all the way up to the full three-dimensional chip stack. Let's begin. This slide reveals the most important insight in the entire field of silicon quantum computing. A classical CMOS transistor and a quantum dot are built from exactly the same material layers. On the left, we have the classical transistor. Notice the three layers: metallic electrodes on top, insulating oxide in the middle, and a silicon substrate at the base. When a voltage is applied, a large current of electrons flows through the channel. This is classical binary switching, the foundation of every computer chip today. Now look at the quantum dot on the right. The material stack is identical, same electrodes, same oxide, same silicon. But instead of switching millions of electrons, we are trapping just one single electron, shown here as this glowing teal sphere. The insight in this callout box is the foundation of this entire field. Silicon quantum computers repurpose the existing CMOS fabrication infrastructure. They do not replace it. Before we can build a spin qubit, we need to choose the right host material, and that choice turns out to be one of the most consequential decisions in the entire engineering stack. On the left is gallium arsenide. It has excellent electron mobility, but look at that chaotic red crystal structure. Every single atom in the lattice carries a nuclear spin, creating a constant magnetic noise bath that rapidly destroys qubit coherence. It is disqualified. In the center is natural silicon. Far better CMOS compatibility, but natural silicon contains 4.7% of the silicon-29 isotope, and those silicon-29 nuclei each carry a nuclear spin that interferes with our electron qubit through hyperfine coupling, causing rapid decoherence. Still not good enough. The winner, highlighted here in teal, is isotopically enriched silicon-28. Every silicon-28 nucleus has zero net nuclear spin. This creates what the field calls a magnetically quiet environment, dramatically longer coherence times, while remaining fully compatible with standard CMOS fabrication. This material is the non-negotiable foundation of competitive silicon spin-qubit technology. Now we understand the material. Let's look at how a spin-qubit device is physically constructed layer by layer, from the bottom up. At the very base is the intrinsic silicon substrate, the mechanical foundation and electrical isolation layer. Above it sits the most critical layer, the enriched silicon-28 quantum well, just 10 nanometers thick. This 10 nanometer dimension is marked here. This razor-thin layer is where our electron spin qubits actually live. Above the quantum well is the silicon germanium and silicon dioxide barrier insulator, which creates a potential energy wall that keeps electrons confined vertically inside the quantum well. Next is the aluminum oxide insulating layer. This electrically isolates the control gates from the semiconductor below, preventing unwanted current flow. And at the very top are the aluminum top gates. These nanometer-scale metallic electrodes are the knobs we turn to define and control individual quantum dots below. The concept here is called z-axis confinement. The ultra-thin quantum well traps electrons in a flat two-dimensional plane, reducing a three-dimensional problem to 2 dimensions, setting up the lateral gate control we will see in the next slide. This is a cryogenic blueprint, meaning this device operates inside a dilution refrigerator at temperatures colder than outer space. Now we see how the top gates actually create a single trapped qubit. These gold-colored gates are the plunger gates, biased at positive voltages. They attract electrons downward, pulling them toward specific locations beneath the surface. The red gates are the barrier gates, biased at negative voltages. They repel electrons, creating electrostatic walls between regions of the quantum well. The interplay between these two gate types creates a zero-dimensional potential minimum, a quantum dot, right here at this intersection point. And inside that dot sits a single trapped electron, our qubit, shown as this glowing teal sphere. This is labeled the trapped qubit, the electron cloud. That single electron's spin state, up or down, is our logical 0 and 1. The entire gate array spans just tens to hundreds of nanometers in width, well within the capabilities of advanced semiconductor lithography. And because the quantum dots are defined purely by voltage, they are fully reconfigurable in software without ever touching the chip. Now that we know how to trap an electron, we need to decide how to encode quantum information in it. This slide presents two competing strategies, each with distinct trade-offs. On the left is the single spin qubit, proposed by Loss and DiVincenzo in 1998. One quantum dot, one electron. The qubit is encoded directly in the spin state of that single electron. Control is achieved by firing microwave pulses at the electron's Larmor frequency, combined with a cobalt micromagnet placed nearby to create a local magnetic field gradient that enables electrically driven spin resonance. The key advantage, an extremely small physical footprint. On the right is the singlet-triplet qubit. This uses two quantum dots, each holding one electron. The qubit is encoded in the joint spin state of the pair, the singlet state versus the triplet state. Rather than microwave pulses, control is achieved by electrically pulsing the barrier gate between the two dots, modulating the exchange interaction energy, J shown here. No microwaves required, pure baseband electrical control, making the electronics dramatically simpler. The trade-off is that each logical qubit now occupies two dots instead of one. Both approaches are being actively developed in leading research groups worldwide. We have our qubit, but how do we actually read out its state? This is surprisingly difficult. The magnetic moment of a single electron spin is far too weak to measure directly. The solution is this device, the single electron transistor, or SET, shown here as the central gold structure on the chip. It is an ultra-sensitive electrometer that can detect a charge change smaller than a fraction of an electron. Here is how readout works. A voltage is applied to lower the tunnel barrier just enough that if the electron is in the spin-up state, it has sufficient energy to tunnel out of the quantum dot. A spin-up electron tunnels out, labeled here as spin-up only, traveling through this energy filter. The SET immediately detects the missing charge as a sudden shift in its source-drain current, shown in this readout waveform box. The current jumps from one level to another in microseconds. A spin-down electron lacks the energy to tunnel, so no current shift occurs. The result is a fully electrical readout of the quantum spin state. No optics, no microwaves for readout, just a current measurement. This method is called spin-selective tunneling, or Elzerman readout, and currently achieves fidelities above 99% in the best silicon devices. We now reach the biggest engineering crisis in the entire field, the dense wiring bottleneck. This is the problem that stops silicon spin qubits from scaling beyond a few hundred qubits using conventional approaches. The crisis, described here, has two parts. First, silicon spin qubits are incredibly dense quantum dots spaced at roughly 100 nanometer pitches. But each qubit needs multiple independent, precisely controlled microwave and DC voltage signals delivered from room temperature electronics. Second, and critically, each signal cable conducts heat down through the cryostat. Standard thermal modeling shows that copper-nickel signal lines generate both passive conduction loads and active dissipation. As more cables are added, the total heat deposited at the 20 millikelvin mixing chamber, where the qubits live, eventually overwhelms the available cooling power of the dilution refrigerator. This thermal overload gauge is not decorative. The theoretical hard limit for this brute force approach is approximately 140 to 200 qubits. That is nowhere near the millions of qubits needed for fault-tolerant quantum computing. This bottleneck is not a temporary engineering inconvenience, it is a fundamental architectural wall. Every slide that follows is devoted to tearing it down. The first breakthrough solution: rather than routing thousands of wires to tightly packed qubits, we physically move the qubits themselves to where the wires are. This is electron shuttling. Here is the concept. Resistive top-gate electrodes are used to create a one-dimensional potential channel, like a conveyor belt, that physically carries an electron wave packet along the silicon surface. This arrow shows the distance, 100 micrometers from a source dot to a target dot. That is enormous by quantum dot standards, allowing full control wiring to be routed in the space between qubit zones. But here is the critical physics question. Does the spin state survive the journey? The answer is yes, and here is why. While the electron's momentum is constantly randomized by scattering, making transport momentum incoherent, the spin state is protected by motional narrowing. Motional narrowing works because the electron moves through many different nuclear spin environments faster than any single nucleus can affect the spin. The fluctuating noise fields average to near zero over the transit time. The result: spin coherence is maintained over distances up to 15 millimeters, a macroscopic scale that far exceeds any chip-level requirement. Shuttling decouples qubit density from wiring density, and that changes everything. Controlling a spin qubit requires a sophisticated signal chain that spans more than 300 Kelvin of temperature, from room temperature down to the millikelvin qubit chip and back. Let's trace it from left to right. The chain begins here with room temperature digital-to-analog converters, or DACs. These generate the precise microwave pulse sequences that define quantum gates and the DC bias voltages that configure the quantum dots. Next are the signal attenuators. As signals travel down through progressively colder cryostat stages, these attenuators reduce power and, critically, thermalize the electromagnetic noise on each line to the local temperature, preventing room temperature photons from reaching the qubit. The conditioned signals then reach the qubit drive lines and resonators on the chip, delivering gate pulses to the gate electrodes. Now the readout signal travels back, and this is where the traveling wave parametric amplifier, the TWPA, becomes essential. The TWPA operates at millikelvin temperatures and amplifies the microscopic readout signal, equivalent to a single microwave photon, by roughly 20 decibels, using nonlinear superconducting parametric gain without adding significant thermal noise. Without the TWPA, the signal would be completely buried in noise before it reaches the next stage. Finally, low-noise amplifiers at the 4 Kelvin stage provide additional gain before the signal returns to room temperature digitizers for classical processing. This slide presents the solution that the entire field believes is essential for scaling beyond a few hundred qubits. Cryo-CMOS, classical control electronics, moved physically inside the dilution refrigerator. The breakthrough is conceptually elegant. Instead of running thousands of individual microwave cables from room temperature all the way down to the qubit chip, we cut those cables and replace them with a classical control computer installed at the 1 to 4 Kelvin stage of the cryostat, where the cooling power is orders of magnitude greater than at the mixing chamber. The specs define the engineering challenge. These custom integrated circuits, called cryo-DACs, must operate correctly at cryogenic temperatures, where standard CMOS transistors behave differently than at room temperature. They generate all the required microwave pulses and DC bias voltages locally, distributing them to the qubit chip through short local interconnects. The defining constraint is power. Each cryo-DAC chip must dissipate less than 2 milliwatts total. That ultra-low budget drives the circuit design toward highly specialized analog and mixed-signal architectures that are fundamentally unlike high-performance classical chips. The payoff: one cryo-DAC chip can serve dozens to hundreds of qubits, reducing room temperature cables by potentially 2 orders of magnitude. Cryo-CMOS is the key that unlocks the door to million-qubit silicon processors. This is the synthesis slide, where everything comes together into the complete architecture of a future silicon spin-qubit quantum processing unit. The solution is a three-dimensional heterogeneous chip stack. At the top is the brains, the Cryo-CMOS control chip. This classical integrated circuit generates all gate pulses and processes all readout signals, operating at the 1 to 4 Kelvin stage. Below it is the high-density interposer, a passive wiring substrate that routes thousands of signals between the control chip above and the qubit chip below with extreme density. This is the core, the quantum qubit chip. This layer contains the enriched silicon 28 quantum well, the nanometer scale gate arrays, and the SET readout sensors, all operating below 100 millikelvin. At the bottom is the PCB and heat spreader, the mechanical package that provides macroscopic electrical connections to the outside world and thermal anchoring to the dilution refrigerator cold plate. These vertical pillars threading all layers together are through-silicon vias, or TSVs, conductive channels etched through the silicon carrying signals between stacked layers with micrometer-scale path lengths. The key architectural insight: the wiring bottleneck is solved not by better cables from room temperature, but by bringing the classical control hardware physically adjacent to the quantum hardware, separated by micrometers, not meters. The three-dimensional chip stack creates a new engineering problem that must be solved before any of this works: an extreme thermal gradient between two chips separated by just a few hundred micrometers. The Cryo-CMOS control chip operates at approximately 1.5 Kelvin, shown here in warm orange, radiating heat. The qubit chip below must be kept below 100 millikelvin, shown here in cold blue. That is a temperature ratio of more than 15 times across a microscopic gap. The engineering challenge is described here. If even a small amount of heat flows from the control chip down to the qubit chip, the electron spins become thermally excited above the Zeeman energy splitting, and qubit coherence is completely destroyed. The solution is this middle layer: thermally isolating spacers and superconducting microbumps. These interconnects are engineered to efficiently conduct electrical signals while acting as thermal insulators, blocking phonon heat transport from the 1.5 Kelvin layer to the sub-100 millikelvin qubit layer. The solution text here describes the simultaneous optimization required. Maximize electrical signal bandwidth through the interconnects, minimize thermal conductance across the inter-chip gap, and maintain nanometer-level mechanical alignment across the entire chip area. This thermal management challenge is one of the most active materials engineering problems in the silicon spin-qubit field today. With all the technologies in place, enriched silicon, electron shuttling, Cryo-CMOS, and 3D packaging, we can now see what the complete scalable processor architecture actually looks like. This is the unit cell blueprint. Each unit cell in this grid occupies a footprint of just 10 micrometers by 10 micrometers. The full processor is a repeating two-dimensional tile of these cells, like a memory array, but for quantum information. Within each unit cell, data qubits, shown here, store and process the actual quantum information during computation. Ancilla qubits here are the auxiliary qubits used to measure error syndromes in the surface code error correction protocol, without disturbing the data qubits. The load and readout SET zones are where spin states are measured at the end of each error correction cycle, using the charge sensor readout method we discussed earlier. And these T-junction shuttling buses are the electron conveyor pathways, branching channels that route electrons between unit cells in 2 dimensions, connecting every qubit zone across the entire chip. This architecture directly implements the surface code, the leading quantum error correction protocol, because it naturally forms a 2-dimensional lattice of data and ancilla qubits with nearest neighbor interactions. Tile this structure across a chip, and you have a path to the millions of physical qubits required for fault-tolerant quantum computing. We end with the complete semiconductor quantum blueprint, 4 engineering pillars that together define a manufacturable, scalable path to fault-tolerant silicon spin-qubit quantum computing. Pillar 1, material. Enriched silicon 28 provides a zero nuclear spin host that creates a magnetically quiet confinement environment, extending electron spin coherence times by orders of magnitude compared to natural silicon or gallium arsenide. Pillar 2. Scale. Resistive electron shuttling maintains spin coherence over distances up to 15 millimeters, breaking the 100 nanometer density limit and allowing control wiring to be routed without crowding the qubit array. Pillar 3. Control. Millikelvin Cryo-CMOS circuits co-located with the qubits inside the cryostat eliminate the thousands of room-temperature coaxial cables that impose a hard ceiling of roughly 140 to 200 qubits in conventional architectures. Pillar 4. Architecture. Three-dimensional heterogeneous packaging. Stacking the Cryo-CMOS control chip, the high-density interposer, and the silicon 28-qubit chip via through-silicon vias enables the dense, tillable unit cell layout required for surface code fault-tolerant error correction. Together, these four pillars form a coherent engineering roadmap. And uniquely among quantum computing platforms, every one of them builds directly on 6 decades of classical semiconductor knowledge, tooling, and global manufacturing infrastructure. The quantum computer of the future may well be built in the same foundries that make your phone's processor today.